I am Dr. Anju Tamar, Associate Professor in Physics in MSJ College, Bharatpur. The topic which we are going to discuss today for MSc classes is surface distribution of charges and dipoles and discontinuities in the electric field and potential. So in electrostatics, we have to find electric field or the potential due to given surface distribution of charges. And for this purpose, Gauss's law is used in case we are going to find field or the potential. So in this particular article, we are going to discuss the discontinuities in the electric field and potential. So let us consider a surface S with the unit normal and directed from side 1 to side 2 of the surface as shown in the diagram, and sigma x is the surface charge density and E1 and E2 are the electric fields on either side of the surface. So here while using Gauss's law, we can easily find that E2 minus E1 dot n cap, that comes out to be equal to sigma over epsilon naught. So here we get this equation 1, and it is clearly showing that there is a discontinuity of sigma by epsilon naught in the normal component of electric field while crossing the surface along the direction of unit normal n. Now for any closed path, we know that the line integral along the closed surface of the electric field E dot dl will vanish as given in equation number 2. So using equation 2, we can find that the tangential component of the electric field is continuous across a boundary surface. And what about the potential? The potential can be written as phi of x So the potential phi of x is equal to 1 by 4 pi epsilon naught, and this is integral over the surface S sigma x dash, and in the denominator we have modulus of x minus x dash dA dash as equation 3. And this potential is everywhere continuous for volume or surface distribution of charges and even within the charge distribution itself. However, in case of point or line charges or dipole layers, the potential no longer remains continuous. So let us see the potential due to a dipole layer distribution and try to find out what happens for potential when we cross the layers of the dipole. Now for making a dipole layer, we can imagine a surface S having surface charge density sigma x on it and another surface S dash lying close to S and having an equal and opposite surface charge density on it at neighboring points as shown in this particular diagram. We are having two surfaces S and S dash nearby, and sigma x positive surface charge density on S and negative equal and opposite negative surface charge density on S dash separated by distance small d of x. The dipole layer distribution of strength capital D of x is formed by letting surface S approach infinitesimally close to S dash, while the surface charge density becomes infinite in such a manner that the product of sigma of x and the local separation small d of x of S and S dash approaches the limit capital D of x. So which we can call as the surface dipole moment density. So the limit small d of x tending to 0, sigma of x small d of x equals to capital D of x, the surface dipole moment density given by equation 4. And the direction of the dipole moment of this dipole layer is normal to the surface S, and it is in the direction going from negative to positive charge. Now the potential due to two closed surfaces. So what we consider, in order to find the potential due to two closed surfaces, see the diagram where a part of this dipole layer has been considered, and here you can say that dA dash is at a distance the vector x dash, and for this dA double dash area it is x dash minus n or dx dash, and the separation between dA dash and dA double dash is d or small d of x. So the potential due to these two closed surfaces, that becomes phi of x is equal to 1 by 4 pi epsilon naught line integral over the surface S sigma of x dash x minus x dash dA dash minus 1 over 4 pi epsilon naught, and the integral over S dash sigma x dash x minus x dash plus n times small d and dA double dash equation 5. So here we can expand the denominator of the second term of equation 5, because this small d is a very small value. So for example, if we have this x plus a inverse expansion, where this modulus of a is much less than modulus of x, then we can write Taylor series expansion of 1 over x plus a modulus as 1 over x plus a dot del of 1 by x plus so on. So similarly, we can use this for the second part of the integral in equation number 5, because we have that denominator. We treat the denominator in the same manner. So for d tending to 0, the potential from equation 5 will become phi of x is equal to 1 by 4 pi epsilon naught, and this is line integral over surface S capital D of x dash unit normal and del dash of 1 over x minus x dash and dA dash. So this equation 6 shows that this is the potential of a point dipole having dipole moment given by vector p, which is equal to n times d capital D dA dash. So the potential at x caused by a dipole P at x dash is phi of x is equal to 1 over 4 pi epsilon naught, and the dipole moment P dot x minus x dash over x minus x dash modulus cube given by equation 7. And from equation 6 we can write the unit normal n dot del dash 1 over x minus x dash dA dash as equal to minus cos theta dA dash over x minus x dash modulus square, and this is equal to minus d of omega. And here this d of omega is the element of solid angle subtended at the observation point by the area element dA dash as shown below. So we can clearly see that where the d omega is. So it has been it is the solid angle subtended at the point of observation by the area element dA dash. So now the potential can be written as phi of x is equal to minus 1 by 4 pi epsilon naught integral over surface S capital D of x dash into d omega. So equation 9 is giving us the value of the potential. And for constant surface dipole moment density capital D, the potential is just the product of the moment divided by 4 pi epsilon naught and the solid angle subtended at the observation point by the surface regardless of its shape. This is what equation 9 tells us. So there is a discontinuity in potential while crossing the double layer, and this can be observed by letting the observation point come infinitesimally close to the double layer. Now if we imagine the double layer to consist of two parts, one being a small disk directly under the observation point, then being sufficiently small the disk is almost flat and has constant surface dipole moment density capital D. The potential can be obtained by linear superposition of the potential of the disk and that of the remainder. And from equation 9 it is clear that the potential of the disk alone has a discontinuity of capital D by epsilon naught in crossing from the inner to the outer side. So which being minus D by epsilon naught on the inner side and plus D by epsilon naught on the outer side. Hence the potential of the remainder alone with its hole where the disk fits in is continuous across the plane of the hole. Consequently, the total potential jump in crossing the surface becomes phi 2 minus phi 1 equal to capital D by epsilon naught. And this result is similar as we have obtained for the discontinuity of electric field in crossing a surface charge density. So equation 10 can be interpreted as a potential drop occurring inside the dipole layer.